Okay, back to limits. All right, so here's what we're going to do. There's a little think about to begin with here, and I want you to think about this really, because this is really what leads us into the thinking of limits, which leads us into derivatives, which is a whole half of the course. So we've got this little problem, right? Mr. Record drives exactly 700 miles, and it takes him 10 hours. What can you say? First of all, what is velocity? That, we can think about that like speed, right? So what's his average velocity or his average speed as he goes? So we can assume that it's 70 miles an hour, right? How did you do that? All right. We actually, what you've really done is found what we call an average rate of change. Okay? We talked about this in pre-cal. Do you remember AROC? And we talked about AROC all the time. What was AROC? Do you remember? Do you remember? It's slope. You're exactly right. It is slope. We said AROC was just another word for slope. But I didn't find a slope here, did I? Yeah, I really kind of did. Because by thinking he ended up 700 miles in 10 hours, but where did he start? 0 miles at 0 hours. So remember what that slope is? Y1 minus Y2 over X1 minus, or we even did it like this. Change in Y over change in X. How they changed. How far did Y is my miles. It changed from beginning to end 700 miles. How did my time change? 10 hours. So really, X is always going to be time. And how do I know my units? Well, look. Miles per hour. Units are going to be crucial in here. We're talking like FRQs. You get a point or lose a point based on your units a lot of times. You can have the complete answer wrong but have the right units and get a point, which is big because all FRQs are worth 9 points. You get a point, but that doesn't sound like much, but if you rock out your multiple choice and then you get a point on each of your FRQs for nothing, I mean, it's pretty... Everything in here, but I'm glad you asked. Everything in here that is rounded, and I will say this a gajillion and a half times, 4 decimal places. If you don't take it out that many, if you rounded 2, even if you were right on an FRQ, but you only rounded 2, you lose your answer point. No. You can always go more, never go less. Unless it ends. So 4. All right. Tell me what we can assume here and tell me why. I'm going to assume at some point he sped, right? Because do you always go... How is she doing that? All right, so we can assume that at some point he's speeding, right? He probably went really slow at some point, but he probably also went... We're going to actually, this is a theorem too. What if the speed limit were 60? He definitely at least one time sped, right? Maybe not the whole time. This is just the average, but at some point he had to hit the average, right? Does that make sense to y'all? You can't have that average and not have at least hit it at some point. That's a lesson for another day, though. Okay, everybody okay so far? AROC is nothing. No, you can't make it. That's his average rate of speed. That doesn't mean that's what he went the whole time. But he had to have gone that. Maybe what if he did 100 miles an hour? He had to hit it. Yeah. Because I'm trying to take it to the mean value here, which is I'm trying to make connections. All right. All right, here we go. We're coming up on a question. You're going to need your calculator too. I hope y'all brought it today. Sorry. I didn't bring mine. Where are all your eggs? All right, tell me this. If somebody will go over there and grab them, I got a crate in that, but you got to lift up the old crate first and it's heavy, and then get the one under it. That second closet. All right. Suppose that a ball is dropped 2,717 feet from the ground. Find the velocity after 5 seconds.
Impossible.
Impossible? I might not. Why is it impossible? What's impossible about that? What? I can't find that velocity at that specific point, right? I don't have enough information, but what can I find? I can find a rock. I can find not the velocity, but the average velocity here. Do you see the difference? A rock is average rate of change. Huh? We'll use a rock a lot. It's even on the AP exam. A rock is. We're going to have to find the average and say, I don't know what the velocity is at 5 seconds, but I could tell you the average because I know it started at 0, right? So I could do that AROC formula again. All right, let's apply this a little bit further. Yes, 2717 over 5.
Why don't you just say that?
Because of what we're going to do with it later. I'm overcomplicating it, and I'm going to show you. I'll show you why. I'll show you why in just a second. Just trust me. Yeah. All right. Look at this equation here. It's a very important equation. First off, not quite. Nice try that. S of t, you will see S of t all throughout this course. S of t always refers to position. It tells me where something is. This tells you that the distance the ball has fallen, or the position, right, how far it fell, is given by this equation 16t squared. Have you seen that somewhere before? Some of you, if you took physics, you might have. And I feel like you should have seen it in another science class too. But isn't that your gravity equation? I feel like y'all did that somewhere. Okay.
I know. I can tell you about H-bonds.
All right. So here's what I'm getting at with this is, remember we were talking about what's the velocity after 5 seconds, and we said, but we can't do that. That's in an instant. Calculus lets us take something at an instant and find the rate of change. Something that I haven't been able to do before. So this is what we're going to talk about. Let's talk about this AROC formula, right? AROC is just what? Starts with an average rate of change, slope, delta y over delta x. So here's what we're going to do. Let's see if this is the rate at which that's where I can tell how far it is. So after 5 seconds, where is it? I would plug in this formula, right? Y'all understand what I'm saying? You'd plug in 5. After 5 seconds, where is it? That's what this is telling me. This is telling me the distance that it's fallen. The distance that it's fallen. Right. So if I said how far, that's not the question I asked you initially, though. I asked you for velocity, right? But what I'm saying is, at 5 seconds, how far had it fallen down? Right? So what should... Logan, read this sentence right here. Read that sentence starting in this case.
2,317.
How far has the ball fallen after 5 seconds? 16 times 5 squared.
400.
323.
400.
A number.
400, right?
What?
Yep, definitely 400.
Okay.
Where?
2,317.
16 times 25, right?
Exactly. That's
So
right.
you said SG is always.
Yes. 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 And you'll be given the equation.
What is this?
400, what was the unit?
Is what a rock. Yes. 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 All right. It's already not going as well as I thought. The unit is feet, yes. Unit is feet, and the time is in seconds, right? All right, so remember we're taught, yes. Remember I asked you initially about velocity, and we said velocity is speed, right? So the unit for the speed or the velocity here would be what? No. Feet per second, right? Feet per second. So I'm going to do change in feet over change in seconds. And here's what I'm going to do. I'm going to try really hard to get really close to 5. So I'm going to do A-Rock maybe between 5 and 5.1. I want velocity. I don't want distance. If I just put 5 in here, that tells me how far it fell. I'm trying to find what is the velocity at 5. How fast is the ball falling?
Divide 400 by 5.
You have to put 5 in there for velocity.
Do you have a velocity equation?
Yeah.
It's just gonna be, it's gonna be the ST, it's gonna be 2717
So 5
minus
squared
the
minus 5,
ST
1, right?
divided by 5.
Where?
What is it?
That's average. That's average velocity over the whole span from 0 to 5. What I'm asking you is instant velocity at 5 seconds, not the average. So,
How do you feel how much
Mr. Right, that's what we're trying to do. That's what calculus is going to come in, and that's what I'm leading you up to. Okay.
How are you supposed to tell in that how much you spent on?
Okay, because it's telling you where, it's giving you an equation to tell you where at a certain time. At 5 seconds, I can tell you how far it's fallen. At 6 seconds, I can tell you how far. At 5.72 seconds, I can tell you how far the ball has fallen, right?
No, but rate of acceleration, you need the mass of.
Not rate of acceleration. You've got to use the right terminology here. This is all to find, rate of acceleration is actually jerk. But we're looking for the rate that it's falling, which is velocity.
What it has to speed up.
That's what it's called.
But you have to speed, it has to speed up as you drop it at max velocity.
I'm not saying it's the max. We'll get to finding maxes in a minute. But we're not finding maxes. Right now,
I'm just gonna say this is essential.
Wait, so wait. We have this, right? What do we do? What do we do with 400 to 5?
okay. Let me just show y'all. I'll get untheoretical. I'm asking you, at 5, how fast is the ball falling? And your answer should be, I have no idea. There's not enough information for me to tell. So here's what I'm going to do. I'm going to do the average rate of change from 5 seconds to, and I'll get really close to 5. So maybe from 5 seconds to 5.1 seconds, I'm going to do the average rate of change. Okay. What's the average speed? Between the time 5, I can do that, right? Right? How do you find A-Rock? Change in feet over change in seconds. Between 5 and 5.1 seconds, how many feet did it change? How in the heck am I going to find that? You have an equation for that. Right? At 5 seconds, how far have I fallen? 400. At 5.1 seconds, how far have I fallen? 416 point what? I don't have my calculator. So how did my feet change? How did the time change? What is the average velocity between 5 and 5.1 seconds? Okay, what do you get? So at 5.1 s, and you can fill this out however you want. I don't know. I'm gonna do this over here. This one.
So the first one is
Hmm? Yeah, so you're taking it out. So this is just to be a chart to help you do what we're doing up here on the side. All right, so yeah, you don't have to use. Remember, this is like a textbook. Some stuff we'll use in it, some stuff, yeah. The 161 came from how much did the speed change? At 5 seconds, it was 400 feet. At 5.1 seconds, it was 416 feet. So how much did it change from here to here? The speed changed 16.6. The time changed 0.1. Okay? Let's take it even further out, okay? Because remember what I'm trying to do is I want to know how fast was the ball falling at 5 seconds. Well, that's the average. At some point between 5 and 5.1, it hit that. That's the average. But what is it actually going at 5 seconds? I still don't know. So what if I take this value, instead of between 5 and 5.1, what if we did AROC from 5 to 5.01? See how we're making that interval smaller and smaller and smaller? You see what I'm saying? Do that one and see what you get. Same way we did before. Remember, we've already got S of 5. We're just going to keep referencing that. But S of 5.01, what did you say you got, Wyatt? 401 point. So now my change in feet is what? 1.6016. How my time change? 0.01. What's my average rate of change or my average velocity here? Do you see what's happening as I close in on that interval? Right now, I'm proving a point. You won't be
Getting smaller.
It is. And
There is no answer.
are you filling that or he's right?
If I were filling in this, I don't really know what how they want you to do that. 5.1 would be 416.16. And then whenever you do the AROC formula, you get 161.6 feet per second. Then if I did 5.01, well, S of 5.01 we said was 401.6016. And when we plugged it into AROC, we got 160.16 feet per second. Please do not freak out if you feel like you are sitting in like foreign language class right now. Yeah. That's the AROC formula. We did it the same way. Oh, you're talking about the 16 T squared? This one? Well, this is after we filled it in. So this is change in distance divided by change in time. And it's setting you up for a derivative. Here's why they're writing it like that. It's setting up. Oh, no, you'll memorize an equation. It's not that equation. It's longer than that equation. Yeah. You're exactly right, Hannah. That's what I was trying to get you to. Good job. Why would you? That's why we need calculus. I'm glad you asked. Because this sucks, right? She said, but wait, Ms. McGee, if we put 5.001, wouldn't we be closer to the actual velocity at that point? Yes. Because if I start out finding the average of this, and then the average between these, close, right. So I'm getting closer to 5, right. Yes.
Yeah. How do you know it's not the
I have to do all this from one.
So you will see these numbers starting to converge to a specific number. In this case, 160 feet per second. The further out you go, it gets closer to that, and you go, oh. This is,
So I can just write 160.
Why couldn't we input the 5.01 value?
because you're trying to find it at 5, not at 5.01.
So you see the S5 and then the 5.
Mhm.
Why can't you put 5.01 there?
You're saying find A-rock between these two instead of finding A-rock between each one of those and 5?
Well, then you're just finding, well, then you're finding the velocity of 5.1 specifically, or 5.01.
Now, I think you might say everyone needs the green one. Where's the green one?
I have the
Yeah.
green.
Shake that green, baby. Okay. Let's keep going. Let's keep going. Let's keep going. Let's shake it for the green. Okay, whatever. All right, look. If this. Oh no, that second page.
Christine, were you doing a TikTok trend with us?
No. My second page did not post on here for some reason. Yeah. We're going to apply this. We got a lot of here. Okay, how are we going to apply this? So here's what a question might look like on the AP exam. This is a non-calculator problem. Yes.
We get a formula sheet?
No, they do not give you a
You don't
formula
get
sheet.
a formula sheet?
Any formula you need. Okay, yes and no. Calculus formulas they do not give you. I will give you a handout when we start reviewing of formulas that you have to memorize and know cold. If there is any type of geometric formula, like they're saying, find the average rate of change of the volume of the cylinder, they'll give you the equation for the volume of a cylinder.
Mr. McGee, you said this class was easier than AP.
It is.
Yeah, so far not even close.
We haven't even, listen, this is just intro, yeah. Trust it. I know, y'all, all these people have not gotten through it all before y'all, and I've taught it so many, I promise, just trust it. Yeah, trust it. All right, look at the question here. I'm almost done with this little section before we get into the real limits. What I really want to look at today. Limits are fun. My kids always score way up here on limits. It does have to do with it, because you have to understand this to-do limits whenever we get to the limits. So we put it in here. What in calculus why do we do it? Okay. Look at this question. We've got this tree, right? This tree that's growing, and the height of the tree at a certain time is given by this okay, there's terminology here you don't understand, and it's okay. Twice differentiable, don't worry about it. I'm going to talk about what that means, okay? Remember, FRQs have multiple parts to it, so part C and D might use that information, but I'm just giving you part C. Okay, so twice differentiable, don't worry about that. H of T is in meters, T is in years. Selected values are given. Now it says use the data to estimate H prime of 6. Now I'm going to tell you, you haven't learned that what that H prime means, but H prime is what we call a derivative, and we'll talk about derivatives, but all derivatives is average rate of change. So what I'm asking you is the average rate of change, and notice it says estimate. So if you want to cross out H prime and put A rock, estimate, use the data in the table. Look at part A. And we're going to think about it as the rate of change. But the rate of change, I said A rock, but it's asking me at a specific point. So it's asking me, listen guys, it's asking me for the rate of change at 6. That's an instant. This is the same thing we were doing with the 5. I don't know 6. Look at my table. Oh no, I don't have a 6 on there, right?
Yeah, you do. What? There's a 6.
There's a 6 in eggs, but not in T.
That's the problem.
Well, then just find the difference between 6 and 11. And
Rate of change. How fast is the tree growing at 6 years? What? There is no 6 years. What can I possibly? You are exactly okay, but no, what? 2 years. Close. 5 years. 5, 7.
I have a second question.
Yeah.
7, 8, 5, and 10.
Yeah.
So you're doing the real change.
Yeah. Okay. All right. Listen. Y'all, you got to focus in. I say this, and you'll hear me say this 100 million times. 100%, 90 minutes. I gotta have it from you. I mean, we've laughed and we've cut up, but I've got to have your attention 9 minutes. Otherwise, you're doing it at home, and I really don't want you doing this at home. I want you doing it here with me. Yeah, it's not bad because we're fixing. We haven't even touched on limits yet. All right. How fast is the tree growing at 6 years? Heck, I don't know. So tell me what you're doing then.
This is 5.
I'm having to average to find it. I'm using A-Rock, and here's the takeaway here. I'm using A-Rock, come on. I'm using A-Rock to estimate what we call I-Rock. What do you think the I stands for?
Instant.
Instantaneous rate of change. I'm using A-Rock to estimate the rate of change at an exact instant. Instantaneous. Okay? So I'm using what I know from Algebra 1 and slope, right, to estimate an instant value. So if I take these values and I do the slope between 5 and 7, do it. Tell me what you get. Okay. Oh, I do have this here. Look. Right? So between 5 and 7. That's what I'm going to use to estimate 6. I don't have 6, but I can go on either side of 6 and estimate and say, okay, well, now remember what it is. Change in this time it's what? H over change in T, which is, how does H change? 5. 5 what? Meters over 2 years. What is the estimate for the rate of change that the tree is growing at 6 years? Which is 2.5 meters per year. This, I'm using these 2 points to estimate 6. You just answered part A, one part of a 4-part FRQ from 2018 on day 1 in calculus. Okay. We're using the data here to estimate the rate of change, right? The rate of change is 6. 6 falls between 5 and 7. So these are the 2 points. So all I do is slope between these 2 points. A-Rock is always slope. So 11 minus 6 over 7 minus 5. That's the answer. That's literally what you do. You have to write that word. Yeah. Or T, we use T a lot. Okay. All right. Not finished it, not yet. All right. We will delve a lot deeper into that soon. If you don't get it, it's okay. I do need you to know and understand what A-Rock is and how you find A-Rock. Okay? Big takeaway there. Yeah. Yes, only when it's spinning. All right. At the bottom of that page, and it looks like it printed over onto the next one for me, but at the bottom of the page, you have some different, some of you said, why wouldn't we just do this? Why wouldn't you just do that? So I'm not going to go over every one of these. I'll put this if I can't for one. But the first column, tells us some things that we did without calculus and how we're going to use calculus now to answer the same questions. Many of the questions y'all are going to get really ticked off. I already know, yes. Because some of the questions you do, if you're really good with your algebra, you wouldn't even need calculus to answer it. But we use calculus because it builds on something bigger. So Because it builds on something bigger to be able to do something later. There's certain, you have to use the calculus. You have to use the calculus. They give a point. They will never say find slope. They will say find the average rate of change. And listen, if I was on this problem, that part A would probably be worth 2 points. You'd probably get 1 point for the answer, which includes the units, and 1 point for the setup of the AROC. So you have to include those units are what I'm getting to. All right, let's talk about limits. Flip it over. Y'all stand up and stretch just a second, even though I don't think you need a break. Stand up and stretch. Take two. Take two. Take two. Yeah. I want you all to take out your calculator for just a minute, and I'm going to have you rewind back and think about the pre-cal stuff. But I want you to input this function right here. Y equals, no, we're going to graph it. I want you to graph that function. Input it in y equals and graph it. Now, as you graph that, there's a picture of it here that's already graphed. You won't be able to see this on your calculator. We talked about it in pre-cal, but there's a funny little hole right here in this graph. Why is that there? It's excluded. Why is it excluded? There's two situations that exclude things from graphs. What are they? Holes, and how do holes happen? You're close. You're halfway there. Halfway there. What you got, Sonny? You're close, but another situation occurs with that too. There's two types of discontinuities that have to do with the denominator. What are they? Holes and that has to do with piecewise. What's an infinite discontinuity? It starts with a V.
B or B?
Reciprocal velocity.
That's not an E.
That's what I said. How did you graph it?
I don't know Apple.
All right.
Vertical asymptote.
Yes. Thank you. All right, everybody listen, because this is that little nugget of information. Remember, there's some things that you really have to remember. This is one of them. Okay? When the bottom equals 0, it creates one of two types of discontinuity. Either a hole or a vertical asymptote. How do I tell the difference? Honey? So if the factor cancels out in the top and the bottom, this is a difference of 2. Same change plus, remember? X minus 1, x squared plus. You don't have to do this for this one. I'm just telling you why there's a hole there. If it cancels, remember, that means there's a hole at 1. And remember, we plugged that hole. We canceled that factor out and went back and plugged that value in. This creates a hole. This is a hole or a vertical asymptote. So if it didn't cancel out, like if I had x cubed plus 7 over x minus 1, the bottom still goes to 0 when x is 1, right? You see that? But nothing cancels. So if I don't like it on this side, I'm going to fall. So if nothing cancels, then that's a vertical asymptote. So remember the difference. So this is a vertical asymptote at x equals 1. This is a hole at x equals 1. If it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote. All right. Now I want you to look at your graph. Now that you know there's a hole there, right? I need to know. Now in pre-cal and in algebra, in pre-cal we plugged the hole. We canceled this out, we plugged 1 back in here to see what this value would be. Do y'all remember doing that? Okay, no, it's
Yeah.
okay. In calculus, however, we are going to use what we call limits. Okay? Limits tell me if I get closer and closer and closer to something, what value am I getting closer to? So as I track this way, as I get closer and closer to 1, what value am I getting closer and closer to on my graph? The whole, which is 3. As x gets closer, take your finger. As x gets closer and closer to 1, what value does the graph get closer and closer to? What if I come in from the other way? What if I trace the graph in this way? Right. What am I getting closer and closer to? 3. That is what we call a limit. So this is how we write it. The limit as x approaches 1. Okay? So this is written on one line, this is below it. Of this function. You can graph this, but this is going to be a lot of look at the graph, analyze, and tell me what
So
the
you
limit is.
literally just write it.
So, yes. Now,
I mean,
So would you just look at the graph?
yes.
So you're right.
Now,
As
for this one, yes. If you look, I think it's, look, something right behind you under unit 1, less than 1, read that. Okay, that's what we did. That's why we did that. All right, read downstairs.
estimating limit value from ground. Wait,
Where's the one for table?
there is no jury. They're both the same.
The point that I'm getting to is, as you read through those, you ask, so we'll have to look at a graph and tell what the limit is. Well, yeah, but you also might have to do it from the table, and you might also have to do it from the table.
Wait, so when there is a limit,
Oh, I
that's
don't
how you
want
have to,
See what I'm saying?
when there is a limit, you're probably, you have to write it like that, or you write it as limited.
They will say, what is this? We're gonna do tons of
And then
that.
you just do equals 3.
Now, but here's what else could happen. Here's what else could happen. They could give you a table, an XY chart, okay? Kind of very similar like what we did with the little, where's that little? Look at this one. This would be an example of using the table to estimate a limit. What is the limit? What is the limit as t approaches 5?
160.
160 feet per second. Right? See how as I'm getting closer to 5, this value is getting closer and closer to its same. I can use a table to show that too. It doesn't have to just be a graph.
So the limit is 160.
All right, let me show you. You got your calculator out, yes. Got your calculator out? No. It's getting closer. Okay, take out your calculator. Take out your calculator. You've already got that function plugged in there, yes?
No, wait, what?
I thought we set my Zoom.
The X.
Did you put it in parentheses, or?
You do, and we use that, but we'll have questions that will not be differentiable in the equation form, and you'll have to do it. All right, so look. You're in your calculator, yes? I'm not even going to take the time to get out my calculator and show you because we're running short of time. All right, so you're in y equals, yes? And you've got your equation. You may have graphed it, you may not have. That's irrelevant. I don't even care what the graph is. And before you go into the table, window, the table set, second window, and make sure you're independent, it says ask and not alright.
How do I get the table?
Wait, mine,
I don't
I'd like
want
to
to
ask one, because I like to.
We needed to ask though, because if you is x approaches 1? You know that from this, but what is from the equation? Remember, your calculator's not graphing holes. So now go into your table. Stop it loading. That is inappropriate, not nice.
We're vulnerable right now.
Second graph. Everybody, second graph.
Second graph.
Okay. What number approaches 1 from this side? Give me a number close to 1 that's not 1. 0.0. Okay, let's go even closer.
You just 0.09.
0.09. Type 0.09 enter.
0.9.
0.9.
That's for our X.
0.9. Put 0.9. Tell me what's Put 0.99.
If you do 0.999,
It's 2.97.
it does it on 1.
2.97.
No.
It just goes to 3. It's almost like I already said.
All right.
Oh, and this is oh, it says error.
One says error. One says error.
If you put in 1, I want everybody, listen, guys, listen. Everybody on that table, hit 1. Hit error. Why is it an error?
Because
You can't hit it. You can't be there, it's a hole. Okay, so we put 0.9, we put 0.99, we put 0.9999. Put 1.0001 and tell me what you do.
Oh, we're just multiplying by
What,
3.
do you see what's happening in the table?
By 3.
What is y getting closer to no matter what side you get to? That is estimating a limit from a table. Okay, that is what it means. You get as close as you can to that number, and you see what we did it in the very first example too. Do you understand what I am saying?
So
No.
it is very something, right?
It is. No.
If you put give you that.
So like, are they gonna say like the hole is at 1? How are you gonna find that out?
What was that? Never the calculator. It could be.
I think we can switch.
All right.
Wait, what did you put for 1? You just put hole?
Let's do one together, and we'll let this one be the last one. Flip it over. We're going to do the one on the other side. Graph the following. Logan, shut up. You're welcome. Here we go. This is the one we're doing together. Find it in your packet, or you can look up here at mine. Logan, if you do that one more time, I'm going to call your mama and make you do that for her and show her what you are doing in my class. All right.
This is calculator.
Then I will make you explain what it means to her. For this one, yes. All right. Logan, I'm going to make your seat be outside the door. You're not going to have to worry about sitting. All right. Graph this function. Graph it on your calculator. As you graph it, yep. Somebody asked, will they tell us the holes? I think that was why it said, will they tell us the holes? Okay, I'm in a time situation. This is a calculator problem. In order to find the holes or the vertical asymptotes on this one, what am I going to have to do? But what if you could graph, but it might not show you the holes? What would I have to do?
The limit.
I would need to multiply out and refactor. What I'm doing is it would be a time constraint for me. So what I'm going to do instead is I'm going to graph this. I'm going to look at what they're asking, and there's some hints here for what you need to change your window to. Remember how we play around with those windows? Hit window. When it's saying what? Now this is different. Look at this limit. What is this limit approaching? Find the limit if x approaches what? Can you see that? Infinity. What does that mean?
No limit.
To the right.
That's the, yeah, it's approaching.
What, tell me what we did in algebra 2 and then again in pre-calc that would tell about the limit as x approaches infinity. We did it, we wrote it a blank.
Scott, what is it? Like,
We did a little four-square chart.
what do you do with that?
Exactly right. In behavior.
What did we do? I'll just kind of.
We're gonna use this.
What do I do? What do I do?
Alright, we're gonna use the table. You can graph it and look. You can graph and look, you can use the table and the table.
I see it where you're.
Alright,
But you have to graph it.
if you graph it, if you look at the graph, what do you think? I'm looking at the limit as x approaches positive infinity. So what is that telling me? To the right. The right side of the graph, what is it doing? Which is?
It goes up.
It's going up. So what is your, I don't know. I haven't graphed it. It's going down.
Going down.
Decreasing. So your guess might be that this is approaching negative infinity? That this equals negative infinity? It's approaching zero.
It's got a vertical. It's got a.
It's approaching an asymptote.
This is supposed to be stuff
Okay, okay. Okay. I know.
Alright, listen.
Yeah, it's reaching out.
Alright, everybody listen, because this is the kind of stuff that, this is the kind of stuff that will throw you that you're supposed to know. Make sure you are inputted into your calculator correctly. Your entire numerator is input, your entire denominator. Make sure you can get things graphed the way they're supposed to be graphed. Look, it's telling you change your x-axis window from 0 to 100,000. And change your y-axis from 7 to 9, 7 to 8. What do you do?
X max is what?
Come on, X max.
100,000. Why did it just give you a
Double the X.
So do we have to find the asymptote?
This kid's not here. It's getting him an
What is this,
I put it like the max and then.
All those are.
Alright, so what, look, but you are supposed to, because look. Right? Alright, listen, the point of this, everybody's quite confused, right?
How do we do the window? How do we do the window?
Hit window.
How to grab it, though.
0 to 100,000 on X, 7 to 9 on Y.
You put it the then and the max.
X max.
Did you write it? A little bit of a heartbeat. Mine just works like this. Heartbeat action.
Here's the point of this, listen. So the question was asked as I do limits. Can I just look at the graph? Okay. Look at the graph and evaluate the limit. I can't, right? I have no earthly idea. Looking at the graph. It looks like a...
I did. That is the change window.
It can't be because you have negatives on there. There's no negatives on there. All right, listen. Listen, I know. I want you to go into your table. Table. The point that I'm getting to with this is you can't always just look at the graph. Sometimes you have to use the table. So here's what I want you to do. In that table, I want you to input these values and see if you can figure out the bigger X gets if it's getting closer to a specific value. You're going to use the table to estimate the limit. What do you get at 1? At 1, put in 1, what do you 24. Everybody should get 24 for that. What do you get at 10? How about 100? It stops at 8. Does it continue to be 8 as you go from there? So what do you think the actual limit is? 8. Could you have gotten that from looking at your graph? Heck no, y'all are wigging out on me. I'm like, nah. Because you can't use the whole point was that you did freak out on it because it's not, you can't do it that way. So you have to go into the table. So I'm getting really close. I'm getting my X closer and closer to whatever it's telling me. And I'm watching what these numbers converge to. Does that make sense? You could keep going, but it's going to
I got
8.
0, 0. I got 0.
Zero?
Zero for all of the bottom.
Does it go to 0? Ooh, what do you think that means?
Jump.
I would say it's probably a jump. I would say it's approaching 8 this way, but it's jumping from this way. Absolutely.
You like that?
Do you see? As you put these numbers in, are you in tables? I think you input your